There are many different types of shell and tube heat exchangers, and each one is designed to accomplish a specific function in a process. In this program, we're going to look at condensers and reboilers, two shell and tube heat exchangers that are designed to do specific jobs. In this part of the program, we're going to focus on condensers. We'll look at how condensers operate in a process, and we'll examine how a condenser can be started up and shut down. We'll also look at some of the basic checks operators should make while a condenser is in service.
These are the learning objectives for this topic. When you have finished reviewing the objectives, select Continue.
Condensers are one type of shell and tube heat exchanger. They're designed to convert gases or vapors into their liquid states. Here's an example of a typical condenser. It's used to turn steam into water so that the water can be reused in a steam generating system. Condensers can also be used to cool and condense product vapors. For example, the vapor produced in this distillation column flows into a condenser and is converted to a liquid. Depending on the process involved, the liquid formed in a condenser may be referred to by different names. What do you suppose the liquid that's formed when steam is condensed into water is called? Very good. The water that's formed when steam is condensed is called condensate. On the other hand, the liquid that's formed when product or byproduct vapors are condensed is often called distillate. To get a better understanding of how a condenser operates, let's look at an illustration of a condenser that uses cooling water to condense product vapors into distillate. This condenser has a shell, tubes, tube sheets, a vapor inlet, a cooling water inlet called a head, a distillate outlet, a cooling water outlet head, and a receiver. On this type of condenser, the cooling water heads may also be referred to as water boxes. During operation, on the tube side of the condenser, cooling water enters through the inlet head, passes through the tubes, and flows out of the condenser through the outlet head. On the shell side of the condenser, vapor passes through the inlet and flows around the tubes. When the vapor comes into contact with the cool surfaces of the tubes, heat is transferred from the vapor through the walls of the tubes to the cooling water. As heat is transferred to the cooling water, the vapor cools and condenses on the surfaces of the tubes. The condensed vapor, or distillate, drips off the tubes and falls to the bottom of the shell. It then flows through the distillate outlet and into the receiver. What do you think the receiver is used for? That's not right. The receiver receives or collects the distillate that drains from the shell of the condenser. The distillate is usually sent on for further processing or to storage. Now, as the vapor condenses, a low pressure is created inside the condenser. This low pressure draws more vapor into the condenser. In order for vapor to continue to flow into the condenser, the pressure inside the condenser must be lower than the pressure of the vapor entering it. Condensers can be operated at almost any pressure, as long as it's below that of the entering vapor. For example, the vapor entering this condenser is at 250 psi, and the condenser is operating at a pressure slightly less than that. On the other hand, this condenser is operating under a vacuum, because the vapor entering it is near atmospheric pressure. In a condenser that operates under a vacuum, the condensing vapor normally maintains the vacuum. However, when the condenser is started up, auxiliary equipment, such as a steam jet air ejector, may be needed to establish the initial vacuum. A steam jet air ejector consists of a steam inlet, a nozzle, a suction port, and a combining tube. Normally, the combining tube is connected directly to a small condenser called an air ejector condenser. During operation, steam enters the ejector through the steam inlet and passes through the nozzle. What do you think happens to the steam in the nozzle? No, that's incorrect. As the steam passes through the nozzle, it is accelerated. As the fast-moving steam leaves the nozzle, it draws air in from the main condenser through the suction port and to the combining tube, where the air mixes with the steam. This mixing process is referred to as entraining. As the steam and air mixture flows out of the air ejector, an area of low pressure forms in the air ejector suction port. This low pressure draws additional air in from the main condenser. This air also becomes entrained in the steam, and the process continues. The final result is that the pressure in the main condenser decreases. In some systems, the air ejector and its condenser are shut down after a vacuum has been established in the main condenser. But in some processes, the air ejectors remain in service to remove air and other gases that won't condense. You see, non-condensable gases can build up inside a condenser. When this happens, the gases insulate or blanket the tubes and reduce the amount of heat transferred in the condenser. As a result, less vapor will condense, and the pressure inside the condenser will increase. The increase in pressure may reduce the flow of vapor, or it could stop the flow altogether. Let's stop here and try a question on condensers and air ejectors. What is the purpose of keeping air ejectors in service after the initial vacuum has been created? That's incorrect. Air ejectors may be kept in service to remove non-condensable gases, such as air, from the condenser. As an operator, you may be responsible for the operation of many different types of heat exchangers, including condensers. So it's important for you to understand how they can be started up and shut down. To get an idea of the steps involved in starting up and shutting down a condenser, we'll watch an operator as he places a condenser in service and then takes it offline. The condenser we'll use in our example is part of a distillation process. It operates at a pressure well above atmospheric, and the cooling in the condenser is accomplished by water that passes through the tubes. Before starting up this condenser, the operator verifies that the valves on the condenser and its associated equipment are properly lined up according to his startup procedure. With the valve checks completed, the operator opens the vent valve on the tube side of the condenser. Then he partially opens the cooling water inlet valve. At the tube side vent, the operator listens for escaping air. What do you suppose the sound of escaping air means? No, that's incorrect. The sound of escaping air means that cooling water is filling the tube side of the condenser. When the tube side is filled, a stream of water flows from the vent. Then the operator closes the tube side vent valve. With the vent valve shut, the operator fully opens the cooling water inlet valve. The cooling water flow is controlled by the outlet valve. So the operator partially opens the cooling water outlet valve to a predetermined position to establish flow through the condenser. At this point, the control room is contacted and the process can be started. When the distillate reaches a predetermined level in the receiver, the distillate pump is started, and the condenser startup is complete. Now, for a condenser that operates under a vacuum, the air ejectors would be started before the process fluid flow is started. This would remove the non-condensable gases from the condenser and create the initial vacuum. In addition to starting up a condenser, operators are also involved in taking condensers out of service. During a condenser shutdown, if the flow of cooling fluid is stopped before the process fluid flow, the condenser could overheat and be damaged. Once the process has been shut down, the condenser can be shut down for maintenance. The operator shuts down the condenser by closing the cooling water inlet valve and closing the cooling water outlet valve. Since the condenser is being shut down for maintenance, the tube side will need to be drained. That's done by opening the tube side vent valve and the tube side drain valve. Once the tube side is drained, the shutdown is complete. In some cases, it may be necessary to purge a condenser with an inert gas after shutdown. Purging removes vapors that could promote a fire when exposed to air. Let's stop here and try a question on the startup and shutdown of a condenser. During the shutdown of a condenser, when should the flow of process vapor into the condenser be stopped? That's incorrect. The flow of process vapor into the condenser should be stopped before the flow of cooling water through the condenser is stopped. When a condenser is up and running, operators regularly monitor its performance. Keeping a close watch on condenser operation can help ensure that the condenser is working properly. Let's take a look at some of the routine checks that operators typically make in order to identify problems and ensure that a condenser operates safely and efficiently. One important check is the level in the receiver. This can be checked using a sight glass on the receiver or from a display or a chart recorder in the control room. If the receiver level is too high, the condenser shell could flood, reducing the condenser's efficiency. What do you suppose could happen if the receiver level gets too low? That's not right. If the level in the receiver gets too low, equipment located downstream of the condenser could be damaged. For example, if the receiver level gets too low, the pump that's used to pump distillate out could cavitate. The cavitation could prevent the pump from operating properly and damage the pump. A controller on the receiver automatically maintains level. An abnormal level could be an indication of a problem with the controller. A low level could also be an indication of a problem with the cooling water flowing through the condenser. Another important operator check is the unit's temperatures and pressures. These indications can be checked on instruments attached to the condenser or on displays in the control room. One pressure reading that is important to check is the receiver's pressure. If the pressure in the receiver drops too low, the product liquid may flash back into a vapor. The condenser's pressure is also important to check. On condensers that operate under a vacuum, insufficient vacuum may affect the efficiency of the condenser. Too little vacuum can result from steam pressure being too low at the air ejectors, from air leaking into the condenser, from too little cooling water flow, or from the cooling water temperature being too high. Many condensers have control valves that regulate the unit's cooling water flow. An abnormal cooling water temperature could be an indication of a problem with the control system or with the cooling water system. Another important check for operators to make is for contamination of the process fluid in the condenser. What do you think could cause fluid contamination in a condenser? That's not right. Contamination in a condenser may be caused by a tube leak in the condenser. One way to check for contamination is to take a sample of the lower pressure fluid and test it for the presence of the higher pressure fluid. In some cases, contamination in the sample can be seen. In addition to sample test results, conductivity and pH readings of cooling water may indicate a tube leak. If there is any indication of contamination, it's important to determine the source of the problem and take the appropriate corrective action. Let's stop here and try a question on the material we've just covered. Which of these choices could be a cause of insufficient vacuum in a condenser that uses cooling water? Good. Insufficient vacuum can occur if the temperature of the cooling water is too high. In this part of the program, we looked at how condensers operate, and we examined some typical condenser startup and shutdown procedures. We also covered some of the basic checks that operators typically make on condensers. Now let's try some practice questions on this material. This condenser is used to condense steam. Select the arrow to where the condensate will exit the unit. No. Remember, the condensate forms on the tubes and collects in the receiver. Try again. Yes, that's it. The condensate leaves the condenser and goes to the receiver. During the startup of a condenser, how does an operator know if the tube side of the condenser is completely filled? Yes, that's it. When liquid flows from the tube side vent, the condenser is filled. Select the indications that can be used to determine whether a tube leak exists in a condenser. No. Try again. No, that's not correct. pH readings and conductivity readings can be used to detect contaminants in the cooling water. Reboilers are heat exchangers that are used to boil or vaporize process liquids. They're used to add heat to distillation columns. In this topic, we're going to look at the operation of two different types of reboilers: kettle-type reboilers and thermosiphon reboilers. We'll also look at some operator responsibilities associated with the operation of a reboiler.
These are the learning objectives for this topic. When you have finished reviewing the objectives,
Kettle-type reboilers are a type of shell and tube heat exchanger. They're primarily used to vaporize process liquids from a distillation column and return only the vapor back to the column. Let's look at an illustration of this type of reboiler to see how it works. The major parts of this reboiler include a shell, a tube bundle, a tube inlet, a tube outlet, a shell inlet, baffles, a vapor outlet, an overflow weir, and a liquid outlet. In this reboiler, steam is used to heat the process liquid. When the steam passes through the tube, it transfers some of its heat to the process liquid. As the steam transfers its heat, it condenses into water, which is returned to a steam-generating system. The process liquid from the distillation column enters the reboiler here. The liquid flows around the baffles and tubes and receives heat from the steam. The overflow weir acts as a dam to ensure that the tubes in the reboiler always stay covered with the process liquid. As the process liquid is heated, some of the liquid boils off as a vapor. The vapor separates from the liquid and collects in the dome-shaped space above the tubes in the shell, and then flows back to the distillation column. The process liquid that does not boil off is pumped from the reboiler and sent to where it can undergo additional processing or be stored. Let's stop here and try a question on kettle-type reboilers. What is the purpose of the overflow weir in a kettle-type reboiler? Very good. The overflow weir ensures that the tubes in the reboiler remain covered with the process liquid. A shell and tube heat exchanger, known as a thermosiphon reboiler, is used to heat process liquid from a distillation column to produce a vapor. Then the vapor and the process liquid flow back to the column. Let's look at an illustration of this type of reboiler to see how it works. The major components of this reboiler include a shell, a tube bundle, a tube side inlet, a tube side outlet, a shell side inlet, and a shell side outlet. In this reboiler, oil that's heated in a furnace is used to heat the process liquid. The hot oil passes through the tubes and is then returned to the furnace where it is reheated. The process liquid from the distillation column enters the reboiler shell and passes around the tubes. Heat from the hot oil vaporizes part of the process liquid. The mixture of liquid and vapor is then returned to the distillation column. The flow of the process liquid and vapor is caused by the difference between the density of the liquid entering the reboiler and the density of the heated mixture that's returning to the distillation column. The heated mixture in the reboiler is less dense than the liquid coming in from the column. This difference in density causes the heated mixture to rise out of the reboiler and return to the column. The result is a natural circulation between the reboiler and the distillation column. Now that we've seen how a thermosiphon reboiler works, let's try a question on this material. This reboiler is used with a distillation column. Select the arrow to the part of the reboiler where the process mixture leaves the reboiler to return to the distillation column. That's incorrect. The mixture of heated liquid and vapor is less dense than the cooler process liquid, so it flows up and out of the reboiler on its way to the column. As an operator, you may be responsible for the proper operation of reboilers. Like other components in a process, reboilers should be checked periodically to ensure that they're operating properly. One important check that should be made is the level in the reboiler. This check is made by observing the level in the reboiler's sight glass. The tubes in a reboiler must be covered with the process liquid. If the level in the reboiler drops too low, the tubes could overheat and be damaged. On the other hand, a level that is too high can be a problem too. For example, if the level in a kettle-type reboiler gets too high, the vapor and liquid will not separate properly, and a mixture may flow back into the distillation column. On a thermosiphon-type reboiler, it's important to check the circulation of process fluid through the reboiler. On thermosiphon reboilers, the circulation is created by the difference between the density of the liquid entering the reboiler and the density of the mixture of vapor and liquid leaving the reboiler. This circulation can be disrupted if the liquid level in the distillation column is too high. If the level in the column rises too high, it can block the reboiler outlet line and disrupt the flow. With both kettle-type and thermosiphon reboilers, instrument readings should be checked frequently. In many cases, the temperature in the reboiler is dictated by the temperature needed in the distillation column. For example, a controller that monitors temperature in this column sends a signal to a steam control valve to either decrease or increase the amount of steam flow to the reboiler. On many kettle-type reboilers, the process liquid is pumped from the column to the reboiler by a pump. The pump should be checked to ensure that it is operating properly. Now that we've seen some of the basic checks an operator should make on an operating reboiler, let's try a question on this material. On a thermosiphon, no, that's incorrect. If the level in the column gets too high, the reboiler return line could be blocked, and the flow through the reboiler could be disrupted. In this topic, we looked at two types of reboilers, kettle-type reboilers and thermosiphon reboilers. We examined the major components of these reboilers, and we saw how they operate. We also took a look at some of the checks that can be made on reboilers to ensure that they're operating properly. Now let's try some practice questions on reboilers. What is the purpose of the dome-shaped shell of a kettle-type reboiler? Yes, that's right. The dome-shaped shell of a kettle-type reboiler provides a space where the process vapors can collect. What causes the circulation of fluids between a distillation column and a thermosiphon reboiler? No. Remember, the liquid flowing into the reboiler is denser than the fluid leaving. No, that's incorrect. The difference between the density of the liquid entering the reboiler and the density of the mixture leaving the reboiler creates a natural circulation through the reboiler in the column. What could happen if the level in a reboiler gets too low? No. Remember, inside the reboiler, heat is No, that's not right. If the level inside a reboiler gets too low, tubes could be uncovered and become damaged from overheating.